In Goal 2 of our study of probability, we're now going to talk about how to compute theoretical probability. With theoretical probability, each outcome in a sample space is equally likely to occur. For example, when you're rolling a die, there are 6 sides and it's equally as likely to roll a 1 as it is to roll a 6. Or when you're flipping a coin, you are equally as likely to flip a heads as you are a tails. Each occurrence for which the outcome is uncertain is called an experiment. Again, remember that probability of an event is the number of successes over the total possible outcomes. Theoretical probability is also known as classical probability. All right, let's look at a few examples. You roll a 6-sided die. Find the probability of each event. So event A would be, what's the probability of rolling a 3? So to talk about notation, the probability of rolling a 3. So P parentheses 3 means we're looking for the probability to roll a 3. Well, on a 6-sided die, how many numbers are the number 3? There's only 1. And we have how many total possible outcomes? We have a total of 6 possible outcomes. So our probability is 1/6, which is approximately 0.167. Remember, with probability will be anywhere between 0 and 1, so double check to confirm that the probability you calculate is between 0 and 1. Event 2, we want to find the probability of rolling a 7. Well, on a 6-sided die, 0 numbers are the number 7. And 0 out of 6 possible, 6 total outcomes is 0. What about rolling a number that's less than a 5? So we want the probability that our roll is less than the number 5. Well, what are the options that we have? We could roll a 1, a 2, a 3, or a 4. So we know that we have 4 possible successes divided by a total of 6 outcomes. This reduces to 2/3, which is equivalent to 0.667. Let's look at example 4. It's a little trickier. You roll 2 6-sided dice. What is the probability of getting a sum of 8? So I'm going to write out each possible scenario here. We could roll a 1, but if we roll a 1, there is no value that we could roll in the second die that would add up to 8. What if we roll a 2? Well, if we rolled a 2, then we could also roll a 6, and that sum is 8. If we roll a 3 on one die, we could roll a 5 on the other, and that sum is 8. If we roll a 4 on one die, we would need to roll a 4 on the other for a sum of 8. If we roll a 5 on one die, we would roll a 3 on the other. And finally, if we roll a 6 on one die, we would need to roll a 2 on the other. So we have a total of 1, 2, 3, 4, 5 options for rolling 2 die whose sum is 8. So as it stands right now, the total number of successes would be 5. Well, now let's talk about the total number in the denominator. We know that our first die has 6 options. Our second die also has 6 options. Now the last thing we need to figure out is, what do we do with the value of these 6s? Do we add them? Do we subtract them? Do we multiply them? Do we divide them? And if we think about the fundamental counting theorem, it tells us that when we have successive events, that we multiply the number of choices in each individual event. So our first die is event 1, our second die is event 2. We have 6 choices in each, so we would multiply those. So our probability is 5 out of 36, which is equivalent to 0.139. Now I'd like to switch gears from looking at a 6-sided die and talk about a deck of cards. I've shown for you in this graphic the sample space for choosing a card from a deck. And the sample space is just all the possible outcomes. And so if you see here, we have 13 red hearts, 13 red diamonds, 13 black spades, and 13 black clubs, for a total of 52 cards. We have 4 aces, 4 2s, 4 3s, 4 4s, and so on, 4 jacks, 4 queens, and 4 kings. I want to also define something called face cards. Face cards are all the cards that have the face of a human, or could have the face of a human. A jack, a queen, and a king are all considered face cards. So when you're finding probabilities, the face cards, you would have a total of 12 of those. 3 in each suit, 4 suits, for a total of 12 face cards. Aces are not considered face cards. Okay, so a card is drawn at random from a standard deck of playing cards. What is the probability that that card is an ace? So we're finding the probability that our card is an ace. We know that we have 4 aces total out of 52 cards, or 1 out of 13 for our probability. As a decimal, that's approximately 0.077. What is the probability that our card is a face card? So we're looking for the probability of a face card. We just discussed that we have 3, 6, 9, 12 face cards out of 52 total cards for a probability of 0.231. What's the probability that our card is a heart? Nope, there's a couple of ways to look at this. You can see that we have 13 hearts out of 52 cards. Or you can look at it as we have 4 different suits. Each shape is called a suit. We have 4 suits, and hearts make up one of those suits, or 1 out of 4. 13 over 52 does reduce to 1 out of 4. So the probability of selecting a heart is 0.25. Example C. Florida's lottery game, Lotto, or however you want to say it, is set up so that each player chooses 6 different numbers from the numbers 1 to 53. If the 6 numbers chosen match the 6 numbers drawn randomly, the player wins the top cash prize. With 1 lotto ticket, what is the probability of winning this prize? So let's interpret what we're being asked to find here. We have to pick 6 correct numbers out of 53 numbers. Whoops. Given that we purchase 1 ticket. So how many chances do we have to pick the winning ticket? So our total number of, our probability of winning, if we purchase 1 ticket, is 1 divided by our total possible outcomes. Well, let's talk about those total possible outcomes. I know that I have 53 numbers and I've got to pick 6 of those. Does the order in which we pick those matter? Let's look back at our question. It says that if the 6 numbers chosen match the 6 numbers drawn randomly, the player wins the top cash prize. It never says that it has to match them in the same order. It just says that the 6 chosen have to be the 6 numbers that are drawn. So order does not matter. So we'll divide by our total. We know that we have 53 numbers to choose from. Because the order does not matter, this is a combination. And how many do we have to choose at a time? We have to choose 6 numbers. So our denominator is 53, choose 6. In other words, we have 1 ticket, so 1 chance to choose the correct 6 numbers out of 22,957,400. That's a probability of 0.0000000437. You can see that it's next to impossible to win the lottery. In example D, as a healthy, non-smoking 30-year-old, your probability of dying this year is approximately 0.001. Kind of morbid, I know. Divide this probability by the probability of winning the lotto game with 1 ticket. Okay, so we're going to take that probability of 0.001 and I'm going to divide that by the probability of winning the lotto. Go ahead and take your calculator and calculate this. So the probability of dying is 0.001, and when I divide that by the probability of winning the lottery with 1 ticket, 22,936 is the outcome. So we can say that a healthy 30-year-old is nearly 22,936 times more likely to die than to win Florida's lottery. Interesting numbers.